right, so section 5.4 talks about sampling distributions and something called the central limit theorem. So sampling distribution says in this section we're going to learn about the relationship between a population mean and the means of samples taken from the population. It says a sample distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. The sampling distribution of sample means is the probability distribution of the sample means. Okay, and here it says the sampling distribution consists of the values of the sample means, x1 bar, x2 bar, x3 bar, x4 bar, x5 bar, so on and so forth. And so if we have a population that has a population mean of mu and a population standard deviation of sigma, then we start taking samples of a particular size, and we find the average of each of those individual samples, okay? It says, considering the random variable x, which is the age of the student in a class. So if I said, okay, everybody, let's see if we can figure out your ages. So Jose, what's your age? Aurora, what's your age? Gilbert, what's your age, right? Everybody else in our class, so just start picking people at random. And it says the range of values may be from, say, 18 to 36. The population mean could be 27 with a standard deviation of 3 years. Now, if we were to take samples of 4 students and we were to find those averages, so if I were to take 4 people in our class and I were to get their ages and find that average, and then do that for different groups of 4, okay? Now, some people might be put in 2 different groups, so I might pick I'm just going to make up names. Brandy, Joe, Aurora, Gilbert, right? And then in my second group, I might pick Gilbert again, Jose, Mel, Melanie, right? So I'm going to be picking groups of 4, okay? And I'm going to find those averages. It says the means of the samples, so those averages, is going to have less deviation because the spread will no longer be from 18 to 36, okay? So let's see. It says here the central limit theorem. It says samples of size when n is bigger than 30 are drawn from any population with a mean of mu and a standard deviation of sigma. The sampling distribution of the sample means approximates a normal distribution. The greater the sample size, the better the approximation. If the population itself is normally distributed, the sampling distribution of the sample means is also normally distributed for any size n. In either case, the sampling distribution of the sample means has a mean equal to the population. So what do we mean by that? I'm talking about this is the mean of the population, okay? Population, that doesn't look very good. Let's see again, population mean. This here is going to be our sample mean. Okay. Let's see. The sampling distribution of the sample means has a variance equal to 1 over n times the variance of the population. So when we have this number here is going to be our variance, population variance, I should say. Oops, variance. When we divide it by n, this gives us our sample variance, okay? And, oops, squared, right? And then this one is going to give me my sample deviation. Okay. Notice what we're doing. We're taking the population standard deviation and we're dividing it by the square root of n, okay? So I'm going to kind of scroll down here and let's see what it says. In other words, the distribution of the sample means has the same mean as the population, okay? So the distribution of sample means has the same mean as the population, but the standard deviation of the sample means will always be less than the standard deviation of the population since we're dealing with the means of the samples, okay? All right, so we're going to take a look at the first problem that we have here. Okay, the first problem we have here says Cell phone bills for residents of a city have a mean of $47. Okay, so that means that my population mean is 47, and we have a standard deviation of $9. Okay, samples of 100, so that's telling me that my n, it's going to be my sample size, is going to be 100. Cell phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. Okay, so all I'm going to do now, my sample means is going to be the same, right? It's still going to have a mean of $47. But the way we're going to compute our sampling standard deviation is I'm going to take 9, okay? Because my formula, actually, you know what, let me write the formula for you guys so you can see it. My formula is going to be standard deviation divided by the square root of n. So my standard deviation is 9 divided by the square root of n, which in this case we said was 100, okay? That's going to give me 9. The square root of 100 is 10, and as a decimal, guys, this is 0.9, okay? So let's see what that means. Before, we had an average of 47, right? So there was my average. And if we add 9 more, look, here's 56. And if we add 9 more, look, there's 65, right? Or if we subtract 9, we can keep going in those directions, right? So the difference between here and here is 9. There's another 9, right? So on and so forth, okay? What we have now is, look, my mean here is still 47. So that's still going to be my mean. But my standard sampling standard deviation is only 0.9. So this number right here, guys, 47.9. The one after that would be 48.6, right? And if I were to go one to the left, it would be 46.1. Let me erase that. Oops, that's not my eraser. There we go. Oh, come on, eraser. There we go. Okay. 46.1. One boy at 48 or 45.2, right? So now notice my standard deviation, right? Talks about the spread. The spread is so much less now, right? Because we are taking sample sizes of 100. Okay, that's the idea. The idea is that my mean is going to stay the same, but the spread in my graph, look how big the spread was here compared to the spread here, okay? So let me keep scrolling here. All right, number 2 says sample size of 64 are drawn from the population in problem number 1. Find the mean and standard deviation of the sampling distribution of sample means. Okay, so remember, we're using the same problem we had before. So my original mean was 47, and my standard deviation was 9. Now, the size of the samples are going to be size 64, okay? So my sampling means is going to be the same as the original one we had. That's always going to be the case, okay? These two numbers, guys, will always be the same. The part that's going to be different is my sample means, my standard deviation of my sample means, okay? This is going to be equal to my standard deviation divided by the square root of n. So we said our standard deviation was 9 divided by the square root of 64. So that's 9 divided by 8. Let me get my calculator. Over here, let's turn it on. Clear it out. What's 9 divided by 8? And 1.125. Okay, 1.125. So what does that tell me? What that tells me is that my mean is 47. If I'm going to add 1.125, this would be 48.125. This one here would be 49.250, right? This one here would be, what's 47 minus 1.125? 45.875. that would be the number that I would have right here. Okay. Right. So again, my spread is still much smaller because my spread is only 1.125, where in the original one, remember the spread was 9, right? The spread was 9. Okay. All right. So let's take a look at the third problem. It says the braking distances from 60 miles an hour to a complete stop on dry pavement of an SUV are normally distributed, with a mean of 154 feet and a standard deviation of 5.12 feet. Okay, so tell me my population mean is 154 feet. My standard deviation is 5.12 feet. Okay. Random size samples of size 12, so that's telling me my n is going to be equal to 12, are drawn from the population. Find the mean and standard deviation of the sampling distribution of sample means. Okay, so the first thing, my mean of the sampling distribution of the sample means is equal to the mean of my population, which was 154 feet. Okay. The standard deviation of my sample means is equal to my population standard deviation divided by the square root of n. So that was 5.12 divided by the square root of 12. So I'm just going to do this on my calculator, okay? So look, 5.12 divided by, if you see where my square root button is, it's right above my x squared, so I'm going to hit second, and then the x squared button, there's my square root button. I'm going to hit 12. Oops, not 15, but 12. Since mine opened up parentheses, I'm going to go ahead and close them off too. And then I'm going to hit enter. And the 2 decimal places, guys, I'm coming up with 1.48. 0.48. Okay. So again, what does that tell me? This number right here is 154. This number here is going to be 155.48. Why? Because I added 1.48 to it, right? This number here, 154 minus 1.48, it's giving me 152.52. That would be this number right here, right? And I could do the same thing for this one here, and I could do the same thing for that one there, and that one there, and that one there, right? But we kind of get the idea, okay? So now we have something called probability and the central limit theorem, okay? So probability and the central limit theorem, it says, in the previous section, we used z-scores to find probabilities for individual members of a population with a normally distributed random variable x. In a similar manner, you can find the probability that a sample mean x bar will lie in a given interval of the x bar sampling distribution. It says to transform x bar to a z-score, we're going to use this formula right here. Okay, so let's see if we can figure this out. It says the mean salary for flight attendants is about $65,700. Okay, so the mean, 65,700. Okay, a random sample of 48 flight attendants. So that's my n, right? We're taking a sample of 48. It's selected from the population. What is the probability that the mean annual salary is less than 63,400? And it's telling me that the population standard deviation is 14,500. Okay, so just like we've been doing, we're going to find the mean of our sampling distribution. Okay, that's the same as the regular mean, which is 65,700. Okay, we're going to find our standard deviation of our sample means, which is going to be equal to our standard deviation divided by the square root of n. That's going to be 14,500 divided by the square root of n, which we said was 48. So let's do that part on our calculator. 14,500 divided by, remember, second to get the square root, right, of the number 48. Since mine opened them up, I'm going to close them off. And I'm going to go to 2 decimal points. So it looks like 2,092.89. 2,092.89. Okay. All right. So we found these numbers now, okay? All right. So the question is asking me here, what's the probability that the mean annual salary of the sample is less than 63,400? So I'm asking, what's the probability that my x is going to be less than 63,400? Okay. What we're going to do is we're going to convert this x value to a z value. Okay. The way we're going to do that is by using this formula right here. So I'm going to take my 63,400. We're going to subtract our mu of x, which was 65,700. Okay. We're going to divide it by our standard deviation of our sample means, which in this case we found to be 2,092.89. 2,092.89. Okay. So let me do this on my calculator. Okay. So first thing I'm going to do, let me clear it out because I got a lot of mess there. 63,400. Okay. Oops, that's too many zeros. There we go. Minus 65,700. Okay. Equals. Now I'm going to divide that by 2,092.89. And I'm coming up with, if I round to 2 decimal places, negative 1.10. Right? So now I'm trying to figure out what's the probability that z is going to be smaller than negative 1.10, right? Okay, so let's think about this. Here's my graph, right? Remember, if I'm thinking about this in terms of z-scores, that's where z equals 0 is. Z equals negative 1.10 would be right about here, right, just to the left of that little 1 mark. And I'm looking for the area to the left, right? I'm looking for the area to the left. Give me 1 second, guys. I'm going to pull up my table so we can see what we're looking for. Okay, so remember, I'm looking for the area to the left of the curve, negative 1.10. Okay, so let me pull up. Here's my z table. I'm going to look for negative 1.10. So, oops. Here's 1.1, right? I want it to be 1.10. So it looks like about 0.1357 according to my table, right? So I'm going to say my answer here would be 0.1357, right? That's doing it using the table, okay? Let's see if we remember how to do it using our calculator, right? If I wanted to use my calculator, remember what I'm going to do. I'm going to go clear. I'm going to go second distribution because I want to get to the vars, right? Second vars. I'm going to go to normal CDF. Okay. Remember, I'm looking for the area to the left. So if you think about this, remember what we're finding? We're finding the area underneath over here. So remember what we put here? A whole bunch of 9s. So I'm going to go negative 9999, right? Comma, negative 1.10. Close it off. Hit enter. And again, if I round to 4 decimal places, 0.1357, right? Because there's a 6 after that other 6. And there's my answer, right? So which one do you like better, using the table or using the calculator? That's really up for you to decide, okay? All right. So now let's take a look at the next problem here. It says, the graph below shows the lengths of time people spend driving each day. We randomly select 50 drivers ages 15 to 19. What's the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Use mu to be 25 and sigma to be 1.5. Okay, so a couple of things we have here. We know that our mu is 25. We know that our sigma is 1.5. We need to find our n. N is the number of drivers that we select. That's 50, okay? So now that we have that, remember, my mu x is the same thing as my mu, which is 25, and my sigma x is my sigma divided by the square root of n, which is 1.5 divided by the square root of 50. So my sigma x is going to be equal to, I'm going to grab my calculator here, let me move it this way, let's clear it out. 1.5 divided by second square root of 50, close it off, and I'm coming up with, if I go just again to 2 decimal points, 0.21, right? 0.21. Okay. All right. So what we're looking for now is it says, what's the probability that the drive time is going to be between 24.7 and 25.5. So what we want to do is we want to convert each of these numbers here to z-scores, right? So remember, the way we convert them to z-scores is going to be x bar minus mu x divided by sigma x, okay? So you know what, that blue is a little light. Let's see if we can go with a little darker blue. There we go, that looks a little bit better. Okay, so here's my first one. We're going to convert this one first. So I'm going to go 24.7 minus my mu x is right here, 25, divided by my sigma x, which is 0.21. Okay, so let me do this on my calculator. Let me move this to the side. So I'm going to go 24.7 minus 25 divided by 0.21. And I'm coming up with negative 1.43. So negative 1.43. Okay. Now I'm going to do this again because I got to do it for this guy. So that's 25.5 minus 25 divided by 0.21. Okay. So let's do this here. 25.5 minus 25 equals, divided by 0.21 equals, and I'm coming up with 2.38. Okay, so what does this mean now? We've converted these x values here to z-scores. So that's saying that the probability is going to be between negative 1.43 and 2.38. Okay, so remember, this is 0, negative 1.43 and 2.38. We're looking for the area in that curve right there. Okay, so guys, I'm going to do this using my calculator because I think when we have these kind of bounds, it makes it a little bit easier to do it on the calculator. So I'm going to pull this up here, right? Okay, clear it out. I'm going to go second vars. I'm going to go to my normal CDF. Okay, my lower value is right there, that negative 1.43. So negative 1.43, comma, my upper value is the 2.38. Okay, close it off, hit enter, and I'm coming up with to 4 decimal places 0.9150. So we would say 0.9150, right? And there's my answer. All right, so we think we got one last problem to do here, and we'll be done with chapter 5. And it says, the weights of ice cream cartons produced by a manufacturer are normally distributed with a mean weight of 10 ounces and a standard deviation of ½ ounce. Okay, so first thing I know is my mean is 10 ounces, and my standard deviation is ½ ounce, 0.5 of an ounce. It says, what's the probability that a randomly selected carton has a weight greater than 10.21 ounces? So notice, we're not taking a group of them, we're taking a single carton, okay? So it's asking me, what's the probability that the weight is going to be greater than 10.21? So what I'm going to do, guys, x minus mu divided by sigma. So I'm going to convert this x value to a z-score, okay? So my x value is 10.21 minus, my mu is 10, my standard deviation is 0.5, okay? So let's take this here, so 10.21 minus 10.21 divided by 0.5 is 0.042. Oops, not 5, I put 5. So 0.21 divided by 0.5. There we go, 0.42. Okay, so 0.42. All right. Now, look at part B. Now part B says we randomly select 25 cartons. What's the probability that their mean weight is greater than 10.21 ounces? Okay, so now we're going to find our sample means, the mean of our sample means and the standard deviation of our sample means. So remember, the mean is the same. The standard distribution of the sample means is going to be 0.5 divided by, that's my n, right? The square root of n. Okay, so let me turn on get my calculator again. Move it this way. Oops. Clear it out. So 0.5 divided by second square root of 25 is 0.1. Okay. All right. So now what we're asking for is what's the probability that this is going to be greater than 10.21? We're going to convert this to a z-score. So we're going to take our x minus our mu x divided by our sigma x. Okay. So 10.21 minus 10 divided by 0.1. Okay. So 10.21, 21 minus 10 divided by 0.1 is 2.1. Okay. Z is greater than 2.1. Okay. So again, here's my Z0, here's Z1, here's Z2. So 2.1 is going to be going this way, right? I'm looking for the area underneath the curve over there. So again, if I do this on my calculator, let me clear it out. I'm going to go second vars. I'm going to go do my normal CDF. Okay. My lower bound is at 2.1, right? Comma. My upper bound, if I'm going to the right forever and ever and ever and ever, we're going to infinity, so we can just put a bunch of 9s. And I'm coming up with 0.02 if I go to 2 decimal places. Or we're doing 4 here, aren't we? So 0.0179. 0.0179. Okay. All right. So let's see. You know what? I just realized something, guys. I didn't finish this part. What's the probability that z is greater than 0.42? I didn't do that here. Okay, so let's do that. So here's 0, here's 0.42. See how this area looks like it's going to be bigger? It should be, right? So let's do the same thing that we did before. Second vars, normal CDF, enter, 0.42, comma, and then a whole bunch of 9s. Close it off. And, okay, this is 0.3372. Okay, this is my answer, right? So let me take off the box off this part because that wasn't my answer. That was just my z value. And then we found the probability of that being 0.3372. Okay, now part C says interpret and compare. Okay, so when we took one box, like we did here, we took one box. That's what we did in part A. When we took one box and we were trying to find the probability that its weight was greater than 10.21, we got something like 0.3372, which is the same thing as 33.72%. So if you randomly select one box, the probability that the weight of that box is going to be weighing more than 10.21 is going to be about 33%, 34%, okay? Now, look what we did in part 2. We randomly selected 25 cartons, right? And we found their weights, and we found those averages. So what this is saying is if we take a sample of 25 boxes, the probability that the average weight of those 25 boxes, that the weight of any one of those boxes in that group of 25 is greater than 10.21 is only 1.79%. Okay? That's what the difference between those two ideas is. Okay? And that right there, guys, is 5.4.